So now let's close out our lecture with Terence. Terence, in deciding where to place you in the roster of guest star lecturers and their cameos, we thought that you would be appropriate for the decision tree and ensembles because you said this features heavily in your research. So can you tell us a little bit about how ensembling does feature in your research?
Sure, I'd be happy to. So I'm sharing my screen and you can see this paper that I wrote back in 2007. That's already more than 10 years ago. This topic is called continuous verification using multimodal biometrics. So let me give you a quick background. Typically, when you use a laptop or computer system, you log in, right? You type in your username and your password. The system verifies you and says that, okay, you're the legitimate user and it lets you use it, right? But suppose after a while, you got up and you left, okay? Or worst case, somebody came and knocked you out and literally hijacked your machine.
It's a little
Now,
bit
your
like
computer
Mission
won't know that.
Impossible, yes.
Won't know that you are no longer there, okay? And so that's a problem, of course. So we looked at the issue of how can we get the computer system to continuously verify the presence of the user, okay? We want to make sure that the legitimate user is still there, hasn't left, and or someone else has not hijacked the system. So that's what we set out to do. And to do that, we had this setup. We set up a camera here. Okay, you see the camera here sitting on top of a CRT monitor. That's an old-fashioned monitor that you don't see. And then a special mouse, which I also have here. Now this mouse is special because right where your thumb is a fingerprint sensor. Okay, so if you're holding your mouse with your right hand, okay, your thumb will be over the sensor, and therefore the system can grab your fingerprint and do verification using your fingerprint. Right? So it's a very clever hardware which we bought from a vendor. So now the question is, how do you combine the face modality and the fingerprint modality? Okay, to fuse them, combine, you fuse or integrate them. These are the various words that we use in order to do a better job to verify the user. Okay, now there's a particular challenge here that may not be so obvious, and that's the following. When you learn about fusion, fusing different features or different signals, the early fusion or late fusion or fusing using the sum rule or by voting, all of that assumes that you have both features at the same time, right? You must have both features at the same time so that you can fuse together.
Right.
But in our case here, that's not happening, okay? Because the camera is capturing the face at a certain time, one image every 2 seconds, that's half a hertz, while the fingerprint sensor is getting a fingerprint 2 images per second, that's 2 hertz, right? So they're coming in at different frequencies and they're not even synchronized. They're not synchronized. So things can come in at different times. So because you don't have the 2 signals at the same time, your traditional method of fusion does not work, right? I hope that's clear.
Yeah. Mm-hmm.
Right. So how do we overcome this? Well, we use something called the hidden Markov model. And as I showed you here, the hidden Markov model, you may or may not have learned it, but it's a standard model to take into account time, right? And so you can see here that the system goes through a sequence of states over time. You can see X1, X2, and so on. These states are unfortunately hidden. So in other words, they're not directly observable. Instead, what you can observe is the observation Z1, Z2, which the system, you can think of the system as emitting or producing that observation as it enters a particular state, right? So therefore now, given the observation, what state is the system in? So in our case, to be precise, we model it with two states, right? As you can see on the slide. A safe state, meaning that the system is safe, the user has been verified, the system is not attacked, so it's safe. And the other state would be attacked, where the system has been compromised, right? And between the two states, you see these edges, these directed arrows. These tell you the probability of transitioning from one state to the next.
Right.
Okay, that's standard HMM setup. Okay, so with this setup, what we're going to do is to do Bayesian inference, right? So given an observation, whether that's a face or a fingerprint, we consider that an observation as an observation of the user, whether the user is there. We infer whether the system is in a safe state or an attack state. Okay, this is standard HMM learning. And so that's how we fuse the different modalities that are coming at different times. Again, and this is necessary because your traditional ways of fusing things, the sum rule, the product rule, the max rule, all that do not work. And so we have to come up with a different way of fusing things. So I hope this gives you a sense of how interesting and how challenging it can be to fuse, to do ensemble learning. You really have to study the problem and understand the nuances and then develop the mathematical and computational structures to do that. All right, back to you, Min.
Thanks, Terence, for that. So for all of us in class, the HMM model is related to things that you've already studied. It's actually a precursor to several machine learning models, including the RNN, which you learned about in deep learning to handle time series data. It's also related, the HMM, to the state machines that you've seen already in the reinforcement learning lecture. Should recall a little bit of Markov decision processes and the build up towards that. With that, we are finished with today's lecture.